All right, it's almost time. May the 4th be with you, everybody. Yeah, I know, but I couldn't resist. Oh, it's always with me. The only question is, which side of it. Yeah, I got it. I'm not sure whether you guys can see my T-shirt or not. There's my T-shirt. Trying to convince a cat to join the dark side. Yeah, it's a picture of Vader holding a cat and trying to convince the cat to join the dark side. I think all cats are on the dark side to begin with, by default. Alright, so we're gonna get started today, and okay, I gotta show you the other one too. I know this is not class relevant, but I'm gonna show you. I'm not sure whether. Okay, can you guys see this? Okay, I'm just checking. Yeah, that's a Lego Vader with a tie in front. So the tie is actually a glued-on tie. Yeah, I call him Corporate Vader. Probably some kind of executive, in a corporation. Got to report to the board of directors, but got a whole bunch of underlings. Have to worry about quarterly earnings. Yeah, that's hard. That is harder than getting the Death Star completed on time. There you go. All right. So what we're going to do today is, I'm hoping all of you are somewhere in the middle of doing the homework that's due on Thursday. And I said last week there won't be any extensions already, so there won't be any extensions. So it's kind of important to get started early and try to utilize the lab time after class today, so that if you run into some unexplainable thing that your program is doing, I may be able to take a look. Not that I'll give you a very direct answer, because most of the time I want to ask you questions so that you can go find the answer yourself. So that's kind of usually what I do. So unless, yes, the Death Star is due on Thursday. Yes, the completion needs to be done. It needs to be, it needs to be completed by Thursday with a functioning planet-killing cannon. So I think that's difficult as well. So on top of that, you also have the homework assignment of this class to complete by Thursday. So there you go. Um, so what we'll do today, what I'm going to do today, is to illustrate, maybe use a few more examples to illustrate, some of the elements that you need to get this homework done. Okay, and I did say some, so not all, but I'm gonna, there's only so much, there are only so many sample programs I can go through to illustrate all of the points. So I'm gonna illustrate one, right now. Yes, Andrew, there's a really quick way to do it, is you type it into a clip if you're using Windows, and you type it into Xclip if you're in Linux. You can probably search for it, how to put a text file into the clipboard, depending on your operating system. So I would just kind of Google search for that. There are easy ways to do it. Okay, there's no need to, yeah. So I would just look it up. All right. So would it be possible to go through what the stack looks like visually when initiating a struct within a subroutine? Okay, we can do some of that. Yes, Omar is correct. In Windows, you can pipe to clip. All right. All right. So, okay. So from the questions, I think we are not connecting a few key concepts. Okay. So there are two really key concepts, and I'm gonna illustrate it here. Okay. So I'm gonna use your regular C inside online GDB for the illustration of most of these concepts, and possibly to do this in assembly. But I think those questions reflect possibly a miss or non-understanding of exactly the same concept in C or C++. So we'll go ahead and see whether that is the case or not. Okay, so I'm gonna do the usual include standard integer.h. So this way I have control over the width of integers. So I'm gonna do a u in 8 underscore t, and we'll make this an array. Okay, so we'll make this r, and it's an array of say 5 characters, and a u in 8 underscore t. We have x, y, and z. Okay, there we go. All right, so this is my struct x, and I'm going to make a very simple subroutine here, which doesn't do a single thing. So f is a void function, doesn't do a single thing. All it does is to do a struct x as a local variable, and we call that r. And inside it would even do some initialization, which ends up being totally pointless. And it would just initialize one of the members. Let's just say member y gets initialized to 2. Okay, there we go. And then main is going to call f. Obviously, that's not going to end up doing anything productive, but that's okay because we are just using this program to illustrate what the stack should look like. Okay, so we put the return 0 back here. There we go. So I'm going to compile this program and see if we can run the program and get to a certain point, get to this particular statement here. Run it. All right. So at this point we have okay. First of all, one of the windows that is really handy, and you don't even have to do BT. You don't have to type BT and then enter in GDB. Is the call stack. So you can see how main is calling f, and this is the right order too, because everything that belongs to f is at a higher address than compared to everything that is in main. No, I take it back. Sorry, I take that back. Okay, everything in main is having a higher address compared to f. Yeah.
Your camera is covering the call stack.
Oh, okay. Sorry about that. Let me. Oh, I can just go ahead and remove. There we go. Oh, still there. There we go. Okay, still covering a little bit because of the date stamp, but I think that's not too bad. All right, so the call stack is right here. It shows that main is frame 1, and then f is frame 0. Frame 0 always refers to the current frame, where we are at, which is right here, and that's why f in this case is in frame 0. And we only have one single invocation of f2. In the case of a recursive subroutine, we might have several instances of, or several call frames of the same subroutine. And the main is one frame away, and that's why it's called frame 1. So in this case, if we want to look at, how the stack is being used at this point in TTP-ASM, so let's go ahead and do that. And I'm going to use a spreadsheet to do it. I'm going to use a localized spreadsheet, because I'm really just using it for drawing a picture. Okay, there we go. All right, so not even having to look at the debugging windows, I can just reconstruct what the stack is going to look like. The highest location of the stack is location FF. Then we have FE, FD, FC, FB, FA, oops, and so on. In this case, main has no local variables, and because main is not really a subroutine in TTP ASM, so main doesn't actually consume any stack space at all. But when we call F, we have to push the return address onto the stack. So the return address back to main is going to be here. So location FF is storing the return address in order for F to know where to go back to in main. We don't have any parameters, and therefore there's nothing to push before we push the return address. If we had parameters or arguments, I should say, if we had arguments to push to pass to function f, then those would be higher than return address. They would be pushed first. And then inside function f, we have local variable r, which is of type struct x. So this is where the two concepts, the two orthogonal concepts are going to be combined into one. One concept has to do with when we have local variables, where are they, and who's responsible to allocate the space for those local variables. And when I say local variables, by default, they are in the auto allocation. They're not static allocation. Okay, so unless you see static, to describe a local variable, they're all auto, which means they're all in the call frame and they're all on the stack. So that's the first thing, is to allocate it. So when we allocate, the first thing we have to ask is how big is a struct x? So I'm going to let you guys think about it and tell me how big is a struct x in this case. And it is correct. So Davesh is correct. It is indeed 8 bytes, and that's with considering that we're gonna make sure that everything is packed. So we have 5 bytes from the array, and then we have 1 byte for x, 1 byte for y, and then 1 byte for z. So when we allocate for the local variables, we just need to know how many bytes are needed as a total. So in this case, we need 8 bytes. So that means I have to keep going a little bit. So we got F9, F8, and I think one more should be enough. So we got F7 down here, 7, 8, 9. Okay, that should be good. So this chunk is going to be 1, 2, 3, 4, 5, 6, 7, 8. Yep. So this entire chunk is going to be for local variable r. And then at that point, and this has to be allocated by the subroutine, because the caller doesn't know how many bytes the subroutine needs for its local variables. So the allocation of local variables is always the responsibility of the subroutine being called and not the caller. To allocate means we just have to move the stack pointer to point to the lowest point of everything that we're supposed to allocate. So that means when we are all done, register D, or the stack pointer, is supposed to point to location F7 in this case, and then we have these 8 bytes allocated for the local variable r, which turns out to be a struct x. So the type of r does not matter as long as we know how many bytes are needed at this point, because we just want to make sure that that many bytes are allocated. So if I were to make these columns a little bit narrower, I can also show you where register D is supposed to be pointing to. So that's basically where register D should be pointing to, is location F7. And when we get into the subroutine, we want to update the y member of the struct x that we know as a local variable r to a value of 2. So now it becomes important to understand how these 8 bytes are, how they're structured. So the allocation, or the way we segment a chunk of memory for a structure, unless you tell the compiler to do something otherwise, typically it is just consecutive allocation. So the first 5 bytes are going to be allocated to R, So that means these 5 bytes are allocated to R, and we can kind of document it and say that this chunk is R. And then the next byte is allocated to member X. The next byte is going to be allocated to member Y, and then the last byte is allocated to member Z. So this is how we know that this particular location FD is corresponding to member Y of the local variable R, which has a type of struct X. All right. Yep, there we go. Okay, I was just checking the text chat to make sure that I'm not missing any questions. So I hope this answers the earlier question of how the stack is supposed to look like. Caleb is typing, so I'm waiting a little bit here. Oh, okay. Yeah, so it's a combination of the concepts, right? Because one concept is the subroutine has to allocate the space on the frame in order to have that space for its local variables. And then the second concept is, when we have a struct, which member occupies which portion of the contiguous chunk of memory for the struct, that would be the second concept. And this is just combining those two. All right, Caleb is asking, how would we figure out the size of a struct if it contains a dynamically allocated array? I believe that is not possible. In other words, in C and C++, this size here has to be known by compile time. I don't think you can leave this one as something that is a variable to be determined. It doesn't have to be on the heap. Okay, so let me just extend this example a little bit, and I'm gonna call the next one Y. Okay, let me stop first because otherwise I can't edit the program. Okay, so if you run into any need where inside the struct you need a pointer, okay, you need an array, but remember in C and C++, an array and a pointer, they really are kind of the same thing. So this time we have R as a pointer to uin8 underscore t, and the rest really doesn't matter. So I'm just going to leave the rest alone. So when we have something like this, the member R of Y is no longer an array of any kind. It is just a pointer, and it is an uninitialized pointer too. So in the case where you want to, I will call this S, R, S, T, and so on. So in the case that you want R of S to point to something that is valid, you can do a dynamic allocation in a normal C program, but at the same time, if you know that the lifespan of the array pointed to by R inside the struct Y only needs to last as long as the struct itself, then what you can do is something like this. So you can have a uint8 underscore t, and we'll call this R2 just to make it super duper confusing. And we'll allocate 256 bytes here, which is obviously undoable in TTP because we only have 256 bytes for the entire thing. But this is a C example, okay? So in this case, you can initialize s.r to be just R. So now from this point on, the ARR member of the local variable S, which is of type struct Y, it's pointing to a valid region of memory at this point. So you can do something like this, and this is not even dynamic allocation because this is assuming we only need this array, for the same lifespan as the structure S itself. Okay, so and that's why it doesn't need to be allocated from dynamic memory, which is either a malloc in C or a new in C++. All right, so there we go. Additional questions. Dynamic has to be heap. So typically, when people say dynamic memory allocation, yes, they usually would refer to the heap, but it doesn't have to be because the counter of dynamic is static. Okay, so anything that is not static is kind of seen as dynamic. So until someone specifies specifically this is allocated from the heap, we don't know whether it's actually allocated from the heap or not. All right, next. Oh, same thing. Yeah, so if it's allocated from the stack, which is in this case, that is still not static, and not static is still kind of falls into the category of dynamic. So it really depends on how you define dynamic memory allocation in that case, because if dynamic memory allocation is anything other than static memory allocation, then this, what I'm doing here, will still fall into the category of dynamic. On the other hand, if dynamic memory allocation is more specifically referring to heap allocated memory, then obviously this one does not fall into that category. So I hope this kind of clears up some of those terms. Are we good? All right. Not seeing any questions. All right, so I'm gonna assume this is okay. All right, so if this is okay, I'm gonna modify this program just a little bit so that we can talk about, so I can actually code it. So I'm gonna code a sample program today that does one thing. Okay, it just appends. Well, let's see. We'll go ahead and initialize a it's not a heap, but it is a pool of available structures. So we are just initializing what we call the free list. Okay. If you have not taken CISP310, don't worry. Okay, I'm not asking you guys to write code for data structure. I'm only asking you to translate code from C code into assembly code. Okay, so we're going to have a value here as usual, and the value can be anything. And then we're going to have a next pointer over here. So it's going to be a pointer, and it is going to be a pointer to a struct x in this case. So this should look really kind of familiar at this point of time, okay, because this is like something that we have done many times already. All right, so now we're going to do some insertion here. Okay, so the insertion code, well, not yet, but I'm setting up to make a linked list. Okay, but the structure is intended to create nodes in the linked list. All right. So now we change function f to do just that. Okay, so the first thing we do is we have a parameter that is called struct x, and then this is star pp, because it's a pointer to a struct x. Okay, that is needed in order to append to the end of a linked list. And then the next one is a pointer to a struct x. So in this case, it is just a single pointer to a struct x. And this is pointing to the structure that we want to append to the end of one level of the reference of this asterisk pp. So the code to do this is going to be, and this time I will do it recursively, but without using the ternary operator because it doesn't make sense. There's no return value in this case. So we'll say if, let's see. Right, okay, so if star pp, then we are not going to insert at this point, and we're going to do it recursively. So we'll call f again, and this time I'm going to use the address of the structure that is pointed to by the pointer that pp points to. And specifically, we are going to pass the address of the member p along as an argument, and we'll just pass the other p along without any change. And then the else case is corresponding to the case where asterisk pp is 0 or null. So that signifies that we are already at the end of the current linked list, and this is the place to append the new structure to it. So the way we append is to say this will get us a pointer to a structure, and oh, okay, I know exactly what to do. It's actually a lot easier than I thought. This is all we need to do. So because PP is a pointer to a struct X, it is actually the address of the member P of another struct X. So by doing this, we are updating the member P of the very last structure of the linked list to point to the new structure that we want to append to that linked list. All right. So if you don't get all of this stuff here, it's not too bad. It's just that we have to know how to translate the code, especially this ugly looking thing. Okay, so we'll get to that point. But I do want to complete the program first. So we're going to have a few structures here. So we're going to have struct X. We'll just have A, B, C, D. And then we have the beginning of the entire thing. So a linked list in this case is basically represented by a pointer to a struct X because it points to the first member, the first node of the entire linked list. All right. So LL is initialized to null to begin with. In other words, the linked list is initially, there we go, empty. So because the only way you can signify that a linked list is empty is the pointer is a null pointer. It's not pointing to any actual node, then it is an empty linked list. So when we need to append to this linked list, we'll call F, and we'll pass along the address of LL, and then we'll pass along the address of one of the structures. Let's say A first. And then we'll want to append B, so we'll call F again. And every time you call F from main, we're always starting from the beginning of the linked list because the main subroutine is not supposed to know how long the linked list is or where the last node is for that linked list. So we'll pass this along. So we have ampersand B, and we'll just do one more time F ampersand LL, and then we'll have ampersand C. Why not? Let me just finish the whole thing. So there we go. All right. So this is the entire program. First thing we want to do is to make sure that it does compile, and we'll check out when it is all done, what is the linked list going to look like. Okay, so we'll put a breakpoint over here, get rid of this one, and just kind of run it at full speed until we get to the breakpoint. All right, so we run it at full speed. Uh-oh, we have a segmentation fault because I passed. Well, that is actually very good. Okay, so now we have a program that is broken in the C code, and that is because I stopped the recursion too late. I stopped the recursion too late because if star pp, so when I get here, star pp is null, and I'm going to store p into where the pointer to a pointer is. And this is also where bt is going to be helpful. So if I do a bt backtrace, sorry, we can see the parameter for each level. And the last one is this one here. And we can see that you can see how the addresses are kind of all right. So pp is that, and then it got changed here. Oh, okay, I know why. I know why it's not working. I forgot to do one thing. I forgot to um, specify the end of the list. So after I do this, I have to specify that p um, because whatever the struct p is pointing to is now the last item. So the next pointer of the structure, so the p member of the structure pointed to by parameter p should be null at this point, because otherwise the linked list doesn't end. It's not terminating correctly. So this is what I forgot to do. There we go. All right, go back to debug. So run the code again. All right. So it does just get to the breakpoint, but it's not the right point anymore. But it's not a bad thing to do, okay? Because at this point we can actually track down LL. So we say print star LL, and star LL tells us that we are pointing to a location that ends with a C0. So we want to see which one of A, B, C, D, this is corresponding to, and I think it is A. So when I say print ampersand A, it does give me, oh, it does not give me the same thing. So it's not A. All right, so is it B? Yep, it is B. That is not what I was expecting. All right, so let's see what B is pointing to. So B, so we look at the P member of B. Actually, it's P dot P. It is D0. So so P is, that looks circular to me. Looks like looks like it is a circular linked list. Let me just double check the logic here. Star PP is P because we want the member of the last link node to point to the new one, and it's initially 0. Alright, so we'll go ahead and put some more breakpoints in here. Start from the beginning and continue execution. So right now LL, star LL should point to the first item. Oh, okay. Alright, so we should say ask what is LL, and it is the address that ends with a B0, and we'll ask is that the address of A, and yes, it is. Okay, so now we continue again, and then we ask what is LL, and it is still pointing to that that location. Okay, so everything is still good. And then we ask what is the next item. The next item has an address of C0, and I suspect that is the address of B. So we ask what is the address of B, and it is the one that ends with a C0. So I made a mistake earlier by looking at star LL. I should just be looking at LL. Okay, so now we look at LL points to P, points to P. So this expression is asking what is the member P. It's LL itself points to the first item, and then LL points to P is pointing to the second item, and then LL points to B points to P is looking at the third item, and it should be a null. Yep, there we go, because we have not run line 38 yet. Okay, so the code is actually doing fine. So we'll put a breakpoint at the return 0. Alright, so now we can look at the entire thing. So we look at LL first, print LL. It is still pointing to, basically it's pointing to local variable A. And then we look at the next one, it's pointing to local variable b, and then if we ask what is the next item, it points to the next one, which is local variable c, and then the next one is going to be local variable d. Okay, so if you're not convinced that this is local variable d, we'll go ahead and print the address of d, and it does match what we saw earlier. And if we ask one more time, then it will give you a null. So if I ask, what is the next one, then it's going to be a null because that's D is the last item in the linked list already. All right. So do we have any questions about this? And I do apologize for the confusion earlier. How does this work? So it might be better to use a picture, but I don't have. Oh, I do. Okay. I don't want to get too much into linked lists because that's a topic for another class. But what I can do is I can show you some pictures. Actually, I'll try to be lazy here. This is a singly linked list. Singly linked list. Append. And we're going to be looking at images or pictures. There we go. So this is the kind of thing that we are looking at. It is also, our head is actually LL. So LL is pointing to A as a structure, and then the member P of A is pointing to local variable B, and then the P member of local variable B is pointing to local variable C, and then the P member of local variable C is pointing to local variable D. We do not have an E, but the idea is the very last item has the member P pointing to null. So that's kind of the picture. And the idea is, when we want to insert items, when we want to append an item, we have to track all the way down to the very last one, and then we have to change this pointer to point to the new structure that we want to add to the list, that we want to append to the list. Yep, it is a chain, but it's a singly linked list in this case, and we're always appending at the very end of the linked list, because there are two ways to add an item to a linked list. We can always add to the beginning, which is the easiest way to do it because you don't have to traverse all the way to the end, but then you'll be reversing the ordering, right? So if we always append to the beginning, it is becoming a stack, because when we remove, we are also usually removing from the head, so that makes it a stack, which means last in, first out. The way I'm doing it, always appending to the very end of the linked list, makes it a FIFO because it's first in, first out. Yeah, so this is a kind of cool concept that you will also be learning how to code it in CISP310. So in this class, I'm not asking you to code it. In this class, I'm coding it, and I'm just showing you what the code is going to look like. Oh, okay, there we go. I just need to remember to save it, so this way I don't lose the content. So I'm going to make this a singly linked list, SLL. All right. So the important part is how do we implement function f in assembly code, okay? Because I think that is going to help illustrate some of the concepts, not all of the concepts, particularly on line 22. What are we going to do with line 22? So let's go ahead and take a look at the assembly code corresponding to function f. All right, I'm just looking for the terminal window that has the right size. I think this is the one, and we'll do it like this. Okay, so on one side we can look at the assembly code, on the other side we can look at the C code. So we just call this sll.ttpasm. And at this point, I'm just focusing on function f. So the first thing we need to do when we look at a function is what is supposed to be in the call frame. And we are not only looking at the parameters, we're not only looking at the local variables, we're looking at the entire thing. So this one turns out to be a little bit easier because we know parameter P is going to be the last item, which means it has the highest address in the call frame because it would be the first item that a caller is going to push on the stack. And then we have PP under that, right under it. And then the caller is going to push the return address right after that. So that means the return address is going to be, in this specific case, 2 bytes below where we can find parameter P. We do not have any local variables, so there's nothing, there's nothing under return address because the subroutine itself does not have any local variables. But if it had, then the local variables will be exactly where the cursor is in the text editor. All right. So knowing this is the picture, I prefer to use labels so that I don't need to remember the actual value, the offset to the items. So I'm going to define, there are several ways to do it. For people who do not like to go all the way from the beginning, they can always just say, f underscore pp is going to be 1, meaning that it is 1 byte from where the stack pointer points to. So if I were to denote, where register D should be pointing to, this is where register D should be pointing to because the stack pointer always points to the last item that was pushed on the stack that has not been popped yet. Okay, so this is, and because D is pointing to the return address, so in order to get to PP, we have to add 1 to the address that D is pointing to. All right, so now we can also say that f underscore p is, I would use an fpp and a 1 plus, just so that it is relative to the offset to access pp. But if you make it 2, it is not wrong. It just means that, if we decide to add more parameters, then you have to change all of them because none of them is relative to the other one. So, either way is fine. All right, so now we get into the actual subroutine. If there were any local variables, I would have to write the code to allocate for local variables here, and then I would need a matching piece of code to deallocate local variables, at the end of the subroutine. But in this case, I don't have any, so I'm not going to put in extra code here. In the past, I put in some extra code even though local var size is 0. So in this case, I'm not doing that. But we also have to remember, how a subroutine is supposed to end. How does it know where to get back to the caller? So the idea is, by the time we get to where the cursor is, register D, the stack pointer, should be pointing to the return address again. So that means we can just use an LD instruction, put that return address into a register, in this case register B. We can use register C as well, and in this case register A is also available because the function returns a void type. So we can also use register A in this case, but it's always safe to use register B, and that's why I said, hey, don't worry about the register A, just keep using register B for this purpose. It cannot be wrong. So that's kind of why I use register B, even though register A can also be used in this specific case. Increment D to deallocate that byte on the stack that was used by the return address, because I have just quote unquote consumed it. It's utilized. It doesn't need to be on the stack anymore. And now I have a JMPB to go back to where I'm supposed to go back to in the caller. All right, so now we can focus on what is actually inside the subroutine. I'm just checking to make sure there are no questions in the text channel, and it looks like we are good. All right. So now we can check whether PP or whatever PP is pointing to is null or not. So this is where it is important for us to kind of keep track of what a register has. Okay, because in the text channel earlier, I think that's the one from the previous class. some people mention, that sometimes they would over dereference and sometimes they would under dereference. I made that mistake earlier too in C code, when I was in the debugger. So it's kind of important to kind of remind ourselves what is in the register, at each point of the execution of the code. All right, so we start with the easy stuff, okay? Because we need PP first, okay? So we'll load f underscore pp into register A. So at this point, A is an offset to pp from where register D points to. Okay, so I'm just going to say dereference D because I'm running out of space, so I don't want to type anymore. Actually, there's no need to use the where, okay, from where, because this indicates where register D points to. So I'm just using a C notation here so I can save a few words. Okay, next we say add AD. So if A was the offset from where the stack pointer points to something that we need to access, by adding the stack pointer to A, now we have the actual address to that something, right? So A is now the address of PP. So at this point, we have to start to pay attention because we have to look at the C code and ask, are we trying to get to ampersand PP? No, that is not the case. We are supposed to get to asterisk PP, which means we need to do at least one dereference. Okay, so we have a LDAA in this case. So by dereferencing, okay, so let me do a dereference of the address of PP. All that really boils down to is just the value of PP, which is a pointer to a pointer itself. Okay. But that is also not what we want, or what we need for the conditional statement. So we need one more dereference in this case, so that now register A has the dereference of PP, and now the content of register A matches what we need in the C code. So that is what I'm talking about, is when you're commenting, don't comment it with just saying, oh, we just add register D to register A. That doesn't help you. It doesn't help you because it doesn't relate the content of a register to concepts, the asterisk and so on, because I need to relate what is in register A to my best ability to what I can express in C or C++. So that is the way I think it would be helpful if you want to kind of comment your program, so that you can keep track of what each register has as you execute the program. Okay, so now that we have asterisk pp in register A, I just need to know whether it's null or not. So that's a trick that we have used again and again, is to use the AND instruction just to force that value through the ALU, and therefore it will update the Z flag, and that's all we need to use in this case. So JCI, we will go to the else case, and I personally would do it this way. I would actually I would just make that label over here, and also make a jump to end if over here, and then make that label f end if over here, and then go back and insert the code over here. In other words, I would make the entire structure for the conditional statement, and then go back and backfill the sections of code that I need to kind of backfill, because this way I won't forget the unconditional branch to branch over the else branch, and I won't forget to make the label definition for f else and also f end if. But this is just the way I write code. If you think this is disagreeable, this is not the way you want to do it, hey, you don't have to do it the same way. Alrighty, no questions yet from the text channel, so I'm gonna continue. So I have to call f recursively, and remember we have to pass the last argument first, so it's just p itself. But p itself, is going to look, kind of ugly, because we have to do something like this: get the offset, get the address, get the value, and now we push the value. So in this case, I did not, explain, every single step along the way, but I encourage you to do that with your program, because I have done this enough to be somewhat confident that this is going to work. But when you're just working on your program and you're not quite sure, it's always a good idea to comment on each line. All right, so this is going to push P, so I'm going to comment after that chunk of code and say, this is push P. Okay, done. Now we have to push that nasty little expression here. Okay, so when you look at something like this, just try to decipher it one level at a time. In other words, don't look at the whole thing and go like, okay, I cannot do this. This is too complex. Well, each level is a concept that you already know. It is just a matter of dealing with one level at a time. Now, with expressions like this, we always work from the innermost part of the expression. In other words, we always look at the most nested portion, which is really just getting to PP first in this case, because everything else hinges on being able to access PP first. So that means we're going to do the LDI A. Now register A is available again because the value of A is already pushed on the stack, and that was the whole deal, right? We have to push P on the stack first. So I can now reuse register A. Okay, this time we're dealing with PP, and we have to do pretty much the same stuff. Okay, there are ways to make it more efficient, but I'm just going to do it in a way that is that's more straightforward. Now, I have already made a mistake at this point. I will explain what that mistake is. This is wrong. This is supposed to be f underscore pp 1 plus. The reason why it's supposed to be f underscore pp 1 plus is because we have pushed an extra item on the stack. So that means the label is assuming register D is pointing to the return address, but at this point of time we have one extra item right below the return address, which is parameter P, that argument P that we are pushing on the stack for the next invocation. So at this point, the stack pointer is actually pointing below, 1 byte below, where the labels, where the label definitions are assuming, and as a result, I can no longer just use f underscore pp. I have to use f underscore pp 1 plus to account for that one extra byte that we have just pushed on the stack. So this is a little bit tedious because you actually have to track all the extra stuff that you have pushed on the stack as you write your code. And this is also why on most architectures there's one thing called the frame pointer, where the frame pointer does not move even after you push items, because it's not the stack pointer. So there's the stack pointer, and then there's also the frame pointer, and the frame pointer is pointing at a fixed place in the call frame. So no matter how many stuff you have pushed afterwards, it will still be the same offset from the frame pointer to various items on the stack. In TTP, we don't have enough registers to do that, and that's why I do not have a frame pointer. So the frame pointer is a convenience feature. You don't need it. You can get by without it. But if you do have it, like the x86 architecture, things get a little bit easier to express. All right, so getting back to here. So what is in A? A is PP itself, okay? But we don't need a PP. We need whatever PP is pointing to. So now we have LDA A again, so that we have asterisk PP in register A. Now, what are we doing with it? In other words, we are now done with the sub-expression of asterisk PP. So what we want to do, and so the first question is, what is it, right? What is asterisk PP? Asterisk pp is a pointer to a struct x. It is the address of a struct x. So what we need to do next is to access member p of the structure that register A is pointing to. Okay? Okay, so let me say that one more time. Now what we need to do is to find the address of member P of the structure that register A is pointing to. Now that makes it easier because we know register A is already asterisk PP, so that's why I changed the way I described it. So you might think, oh, this is nasty because we have to do the access the member and then we have to find the address of that. That is how we see things in C, because in C and C++, finding the address of something looks like an extra step. But in assembly language programming, it is exactly the opposite. To get to the value of something, we have to get to the address first. So this turns out to be quite a bit easier than what we think it would be, because at this point we just have to get to the offset to member P of a struct X. So we'll put it into register B. So assuming an X underscore P is representing the offset to member P of a structure of a struct X, we just load that label or the value of that label into register B. And guess what? This is the unbelievably simple part. We just add those two. So it doesn't matter whether you add A to B or B to A, just whatever is the result, whatever is storing the sum is the one that you want to push on the stack. So now we push this on the stack, decrement D, and then stda in this case. So that would push the address of member P of the structure that PP asterisk is pointing to on the stack. So now we have pushed both items on the stack. It's time to call the subroutine. And to call the subroutine, we have to, there are two ways to do this. Depending on whether you want to load A with a value first, or whether you want to decrement D first. Either way is okay. You just have to remember to use the correct offset in the dot something plus expression. So now we just stda, that pushes the return address on the stack, and now we just continue execution in the subroutine, which turns out to be f itself, but the way we call f does not change even when it is recursive. When it gets back, there's nothing we have to do, because line 22, there's nothing after line 22 in the then branch. The only thing we have to do is to increment D twice in order to deallocate the two arguments sitting on the stack because they are not needed anymore. And then the unconditional branch to f underscore and if is going to finish up the whole thing. So that should do it. And now we get to line 26 of the C code. So we have to get to P first. Okay, so LDI a f underscore P add AD. And then we have LDAA. So that would be P in register A at this point. And we want to store that to what PP is pointing to. So now we have to do LDIB with F underscore PP. Add BD. So B is now the address of PP. LDBB. So that B is now the value of PP. And now we want to dereference. But this time when we're dereferencing, we're not dereferencing to read, we're dereferencing to write, because the asterisk PP is on the left hand side of the assignment. So instead of an LD, we have a ST. So we say store to whatever register B points to, which is actually what asterisk PP is referring to. And then the right hand side is already computed in register A. So that would complete line 26. And then we move on to line 27. The 0 is easy to deal with. Let's deal with the left hand side first. Okay. So to deal with the left hand side, I could have saved a few steps if I were, careful with my registers, so I could reuse a register, but I'm not going to do that. So we'll just LDIA with F underscore P, add AD, and then do LDAA. So register A is now the value of P. The value of P is the address of a struct X we want to only update the member called P of the structure that register A is now pointing to. So it is the same trick as what we did earlier. We load the offset to that member into register B, and then we add the offset to member P to the address of the structure itself. So now register A has the address of member P of the structure that P is pointing to. The two P's are different. One P is the name of a member inside the structure, and the other one is the name of a parameter to this subroutine. And that's why I use f underscore p for one and then x underscore p for the other. So this should make it clear which p we are talking about. Are we talking about the parameter? That would be f underscore p. Are we talking about the member p of struct x? That would be x underscore p in this case. Okay, so we are almost done. We just need to get a 0 into one of the registers. Well, register B is now available, so we can do a sub BB. So this way register B is guaranteed to be 0 after the subtraction. And now we can do STAB to store the 0 into member P of the structure that parameter P is pointing to. So that concludes the else case, and then we fall through to f underscore endif. Basically, that's marking the end of the conditional statement, and then we just return to the caller. All right, so I'm gonna let you guys kind of ask some questions. All right, that's without sounding okay. I'm not gonna go there. So the question in the text channel asks, would LDI B0 also work? The answer is yes. Okay, it would also work, but I choose to use SubBB because one, I want to kind of show you an alternative way to do it, and two, this is actually a little bit faster and it saves me 1 byte. Now, saving 1 byte makes no sense whatsoever when you are working with like 1632 gigs of RAM. But when your entire memory space is only 256 bytes, yeah, that might actually make a difference. So yes, so Victor, you are correct. The LDB0 would also work. That would be the more obvious way to do it too. Okay, Nathan is typing, so I'm gonna wait a little bit as I sip my coffee. Alright, so the next question is, would it have been possible to use register C instead of register B in this example? Yes, indeed. So in this particular example, register A, B, and C are somewhat, I wouldn't say exactly interchangeable because you kind of have to follow the context. But register A, I'll just put it this way: register A is not any more special than register B or C in this particular example because the subroutine F has no return value. So register A is not special in any way. Any place you see the use of register A, you could use register B or you could use register C. You just have to make sure that you're not overwriting a register before its value is utilized. But other than that, yes. All right. Let me take a look at the time. Okay. So I think what we can do is to actually finish this entire program. So I'm gonna go ahead and finish this entire program in assembly code, and then we'll run it. We'll just see whether it works or not. Okay, and I'm gonna share this code with you guys so that you can kind of go back in and comment this code with your own comments. All right. So to finish this program, I just have to define x, and when we define x, it doesn't matter where it is, because unlike a C compiler where it needs a function to be defined before you use the function, before you call the function, in this case we can actually do it in any order. So we start with a no up, JMP to main, so this way I can put f anywhere I want. And then we have x underscore, in this case v being 0 because it is the first member of a struct x, and then x underscore p is the next item, so it's going to be x underscore v 1 plus. The 1 of the 1 plus has to do with the size of member v, and then we have x underscore size being x underscore p 1 plus, and once again this 1 has to do with the size of member p. So now I have basically struct x defined as labels in assembly language. Tag uses -0. I'm not sure exactly what that means, but all right. So now we're down to main. First thing is to initialize the stack pointer. Oh, compiler optimization. No, this program is not even close to optimized, but it is. It's easy to understand. Okay. So when we get here, we have to once again, think about how things are allocated. Okay, so this part does relate to your homework assignment quite a bit. So now we have to look at what the stack is supposed to look like. So we will have A at the top of the stack, then we have B, then we have C, then we have D. Now the way you do this, it just has to be self-consistent. So whether you want to do it in this particular way, it's up to you. Now this is going to take up 8 bytes. No, 2 bytes, sorry, or whatever x underscore size is. There we go. This is going to take up x underscore size. This is going to be taking up x underscore size. This is going to take up x underscore size. This is going to take up 1 byte. So this is the frame of main. Okay, these are the bytes that we have to allocate from the stack, and we want to define these labels A, B, C, D, and LL, or possibly with main underscore as a prefix, so that we can have the same name in different subroutine. Once we use a prefix notation. So in this case, the way I look at this picture is LL is going to be the local variable that is at the bottom of the entire thing. Which also means it has the lowest address. So that means main underscore LL is going to be 0 because it's the lowest item. And then the next one up is D. So we have main underscore D being main underscore LL 1 plus. So once again, this 1 plus is referring to the size of LL, which is a pointer. And all pointers within the TTPSM are 1 byte wide because we use a register to do our dereferencing. Then we have main underscore C. Main underscore C is main underscore D. Now we have to be careful, how to add, what to add to it. Add to main underscore D, because main underscore D, or D itself, is a structure of the size x underscore size. So we have to be careful here to specify x underscore size plus. Now don't use 2 plus, okay? Because if you use 2 plus, then you are assuming that struct x has 2 bytes. So when we need to change the structure, then you're going to have to locate all of those constants and change all of those too. Let's see. Yeah, there we go. Okay, so Rachel is already ahead of me. Then we have main underscore B, and that's just a pattern. Main underscore C, x size plus. Oops, there we go. And finally, we have main underscore A, and main underscore A size. Oh, okay, B, x size plus. There we go. And then we have one more item, which is main underscore local var size. So that's going to be main underscore A and x underscore size plus, because this is basically the number of bytes that we have to allocate for the stack frame for main itself. Now, all of these label definitions does not do a single thing at all at runtime, because labels are a concept or construct that only the assembler understands. Okay, in other words, the Google spreadsheet that we know as the assembler, it understands the label definition, but not Logisim. So when the program is running in Logisim, these labels are gone. Okay, so unless we do something with actual opcode, none of this matters. Okay, because all they're doing is just definitions for us to understand, but it doesn't actually change anything. So this is why we have to do a LDI A with main underscore LVS, and then we subtract that much from the stack pointer. This allocates the local variables. But every time we allocate something, you have to think about when are we going to deallocate it. So we'll put it over here right before the halt instruction at the very end of main. So now the rest of the program is going to go in between. Alright, so now we can get to line 35, which is to initialize LL. To initialize LL to 0, okay, so this part should be getting a little bit boring because we have been doing this for a while already. And then we do a sub BB to make B 0, and then we do ST A B. There we go. So that should implement line 35 of the C code. So from here on, it's really just appending stuff. So I might only do like the first two lines, because if that works, the rest is very likely to work too, because I do want to get to the finish line in this case. And hopefully we encounter a bug, I forget to do something, so I can actually show you guys how to use the trace analyzer to locate problems when we have some mishaps on the stack. So let's hope that this program is not going to work. Alright, so we need to pass the address of A on the stack. So the address of A is a local variable. So that actually means it's really easy to do, because we just say we get the offset into register A. We add we add the stack pointer to A. That's it. That is the address of a local variable, and we just need to push it on the stack. So we say decrement D std A. So that pushes ampersand A on the stack. Next, we have to push ampersand LL on the stack. Kind of the same deal, okay? LDI A with main underscore LL. But remember, we need that one extra one plus, because we have already pushed the address of A on the stack. So we need to account for that one extra byte, that extra 1 byte distance between where the stack pointer currently is and the assumption that we made when we defined the labels. Okay, so that's what the 1 plus is compensating, is because that assumption is no longer correct, because we just pushed 1 extra byte on the stack. But the rest of the code is pretty much the same. Okay, add the stack pointer to the offset, so we actually get to the address. Decrement D, so that we reserve 1 byte on the stack. stda, that's how we push ampersand LL on the stack. And then we have to push the return address. So that's the usual stuff, which is LDIA dot 6 plus. Oops. Dot 6 plus. There we go. Decrement D stda. So now we have all 3 items pushed on the stack. It is time to continue execution at the subroutine, which is F. And when it gets back, we have to deallocate the 2 arguments from the stack. So we have increment D and increment D to do that. So I'm just going to I will test this code first, okay? Because if this part doesn't work, I don't even have to bother to try to append local variable B at the end of the linked list. So let's go ahead and give it a try. Okay, so this is answering an earlier question, is how do we get the content of a text file inside Vim so that we can use the assembler. The way you can do this without even exiting Vim is to say W, which is write, and then the exclamation point is important here because it is piping to a command. Now in my case, it is xclib -cell -clip, okay, space clip. This is Linux Okay, if you're using Windows, it's a lot easier. It's just clip. Okay, this is how we can copy the entire file that you're editing to the clipboard. Then you can paste into the assembler. So I have to change this back because I'm using Linux. So the command is slightly different, like so. And now we can go back to the assembler, which I'm not sure whether it's still up here or not. Doesn't look that way. Oh, this is funny. Okay, this picture is here because Randy Schuster has been using a shark avatar in all of the meetings with the Design Hub. And I mentioned something like, oh, okay, your friendly shark face. So this is the picture that represents a friendly shark face. This turns out to be one of the largest sharks that people have recorded. And they think this is a grandma shark, and it's fairly mellow for a great white shark. It's also one of the yeah, it's kind of funny, but I'm digressing. Okay, I'm just checking out the text channel, make sure that I'm not missing anything important. Alright, so I'm now at the source tab. Okay, get rid of everything in column A, and then Control V to paste in everything. And we'll try to make sure that we don't have any errors. Okay, so just scanning through, no errors. Okay, so we get to RAM file, double check, make sure there's no error here. Oh, that's funny, Aaron. Yeah, Randy really likes that shark avatar, even though there are other ones. I think he used the bear one, initially, and then he just kind of gets stuck with the shark. See, comma separated file. Okay, that sounds good. Save, and then we'll call this sll.csv, singly linked list.csv. Alright, so now we switch back to the command line, which is right here. And instead of messing up with the Vim, I'm gonna switch to another tab to run the program. And I still have not written the script to do this, so yes, I'm just have to do copy and paste a little bit. There we go. This is called sll.csv, and then we redirect the output to sll.tsv. All right, so feels like it comes to completion. No infinite loop. All right, so we'll go to the trace analyzer and make sure that we're in sheet 1 before we import. Oh, by the way, if you go to the general channel of this class, if you go to the general channel of this class, you will find that one of your classmates has written a simulator that has a trace ability as well. So you can use that one instead of this Google spreadsheet approach. So that's no problem. Yeah, the other one is probably easier to use, but I'm so used to this already, so not a problem here. Alright, so we want to replace current sheet, use tab as our separator, and then do not convert. And then we do the import. Okay. There we go. So we'll wait until the progress bar is done, but the summary should tell us how many rows we have, which is 242. That sounds about right. And then we go to analysis, and then we get to that last row first. You can always hope, right? 242, 2, okay, 24, 242, 242. There we go. All right, so this is the end, and the stack pointer is back to 0. So that's very encouraging because if there's some mishap somewhere in the program, it is unlikely that the stack pointer would be going back to 0. We also want to check that location 58 is matching the halt instruction that we have in this program. So we go to the Assemble tab, scroll all the way to the bottom, look at the last location. It is indeed 58. So that's looking good. The program is not crashing into some unknown location and trying to execute some random content in RAM. All right. So now we have to kind of really think about what we should be seeing, on the stack. Okay, so this is where we want to visualize the stack again, and so we have location FF. So this time we'll do a range because we just have, well, actually we don't have that many bytes. So location FEF, FEFF, FD, FC, FB, FA. I mean, I could have used equations or formula to do this. Why don't we do that? I mean, that's just a whole lot faster, right? Okay, so now we look at the value of the previous cell, but we want to convert it back into a value first because in a spreadsheet, FF is known just as a string. It is not an actual value. So we have to convert it back to a value first. So it will dec to dec, okay? Which is a very misleading name because it really is not converting into a decimal number. It's actually converting into an internal representation, which turns out to be a double. So, but that's kind of like, let's not go there for now. Okay, so we're just converting cell A1 into an actual numerical value, and we want to subtract 1 from it. So we want to check that first. Yes, so that is indeed correct. So now we have to convert it back into hexadecimal because that's what we like to see. So we want to go for dec to hex, which is the other way around, and press the enter key. Yes, it is a case difference. I suppose then there might be a case conversion thing that we can do, but I'm not going to go there, okay? Because it's just wasting time. Okay, so this is rather handy. Now we go back to the source code. Okay, go back to the source code, which is here, because I need to refer back to the frame map so that I can see what is supposed to be the last item on the stack. That's A is the last one, or the one that has the highest address, and then B, C, D, and then LL. So now we can switch back to here, and then we can start to label things, right? So we have these 2 bytes. They're basically A. Okay, let's make this even more clear, because this is the second member of A, which is P. This is A.V, and this is B.P, B.V. This is C.P, C.V, D.P, D.V, and then this is LL. Okay, so that's how the stack is being used by main. When we call the subroutine, F6 is going to be used for the last argument, or the second one. So that's going to be the address of A, right? Yes. So it's the address of A, and then the address of A, we know what it is supposed to be already because the address of A is just FE. So location F6. Oh, okay. That's not what I want to do. So this is supposed to be FE. Okay. And then the next one is going to be the address of LL, which is F7. So I'm going to type, what it looks like in C, and in the trace analyzer, what we should be expecting, which is F7. And then F4 is supposed to be the return address. And we know that too. We actually know what the return address is supposed to be. It's just that we have to go back to the Assemble tab, look up. Now this is one trick that that you guys might find useful. is when we locate the line that loads the return address into register A, the second byte is the return address because that's the immediate constant that we are loading into register A, which is pushed on the stack as the return address. So the return address is supposed to be 53. So we go back, oops, not the right window, go back to here. So the next one is supposed to be the return address, which we know is supposed to be 53 in hexadecimal. So this is what the stack is supposed to look like by the time we get into the subroutine F. Because LL is initialized to 0, so we are not expecting any recursive call, and as a result, we should not be consuming the stack anywhere below location F4. Okay, so so when you are debugging your code, you should figure out this entire thing first, okay, because this gives you an expectation of what the stack is supposed to look like, what value should be there, and so on. And also, because we know that LL is initialized to 0, so we also know that this place is supposed to be 0. All of the other ones are uninitialized. So whatever the LogicSim does initialize everything to 0, so we can see a whole bunch of zeros over here. But if LogicSim does not do that, it would be anything at all. Because they're just basically uninitialized. So when the program is done, we know that LL is supposed to point to A. So we know this value, or whatever is at location F7, should become FE. And we also know that A.P is supposed to be initialized to 0. So that would not be visible because it is already 0 to begin with. So when we try to override it with another 0, it doesn't show in the trace. Well, maybe it does, I cannot remember. But it may not show at all because it's not actually a change from a previous value because it was 0 to begin with already. Okay, so when the program is all done, this is what we should be seeing. Okay, a 0 over here, the rest we don't quite know, an FE over here at location F7. And because we don't really have a gremlin running around to mess things up, below where the stack pointer points to, and besides, these are not below where the stack pointer is, while before we deallocate all the local variables. So this is also what we're supposed to be seeing on the stack when the program gets to the halt instruction. All right, all right. So now we can actually go in and see if the program does what it is supposed to. So this is how you debug a program. Okay, you have to really know what the program is supposed to do, and if you're greedy like me, you go all the way to the end and check whether it gets everything done. But if it doesn't, then you kind of have to go back and see where it starts to deviate from what you expect the program to do. That really is kind of how we debug a program. Alright, so getting back to the trace analyzer, we'll go to those locations and see what happens on the stack. Alright, so we're going to look at RAM write, and we can look for a regular expression, which is really handy. So we go to find and replace. And we specifically look for, we specify regular expression like that, and then we specify, we're looking for the asterisk, right? Because when we are overwriting a location, it will start with the asterisk, but we need to use a backslash to escape the asterisk because it means any number of the previous item otherwise, so we have to use a backslash to escape it. And then we have 2 hexadecimal digits, which would be from 0 to 9, A to F, and in this case they're uppercase. There we go. And I think we have exactly 2 of those. So I think the curly brace 2 specifies exactly 2 of those, and then one single equal symbol followed by something that is not a equal symbol. So we have this symbol here. The caret sign means negation of the following. if it is the first thing inside a square bracket expression. So anything other than the equal symbol is fine after the first equal symbol, because otherwise it indicates a read operation. So we are looking for a write operation. So we're looking for one single equal, and then whatever is following the equal symbol is not supposed to be another equal symbol. All right, so let's see if that works. Oh, that works. Nice. All right, so F7 gets 0, 0. So let's go back to our map. Does that make sense? It does make sense, because that's the first thing we do. We initialize LL to 0. So this tells me that when you overwrite a memory location, even if it already had that content, it will still be reflected on column C. Unlike the flags doesn't do that. All right, so the next one I can see here already, location FE is getting, location F6 is getting the content of FE, and that's exactly how we predicted that it would do. So I think we can just kind of scroll down here. F5, location F5 is supposed to get F7 as a value. Location F5 is supposed to get a value of F7. And then location F4 is supposed to get 5.3, and that's exactly what it's getting. And then we should not see any update below that point. So the next update is we actually update LL so that it points to A as our local variable, and that's exactly what is happening here, because according to our forecast, location F7 would change from 0 to FE, and that's exactly what it did. And we should also see a 0 overwriting location FF right after this. There we go, right there. Okay, so after this, we should see no more updates on the stack. Okay, even though the stack pointer is getting changed, no one should be writing to the stack anymore after this point. So all the way to the end of the execution of the program, there should be no more updates, and that's exactly also what we see. So unfortunately, this program did not have a bug, because otherwise I can show you guys, what kind of what kind of sign you'll be seeing, and what each sign would point you, to why the program is not working the way it's supposed to. So unfortunately, this program did not have a bug, so I cannot show you that. All right, so I'm just going back to the text channel. Looks like somebody typed something over there. Regex is cool. You should see Randy Schuster in his shark avatar saying cool, because the shark would actually have the correct mouth shape, when you say cool, just extending the lips and stuff like that. It's really funny, to see a shark avatar to do that. So anyhow, yeah. So anyway, I have just illustrated, this entire program, going from the C code, okay, how you run the C code in C first, okay, in GDB, just so that you understand the behavior of the program. Once you get that, then you move on to the assembly code. But before you even write a single line of code, you have to look at the structure of the stack. Okay, look at the frame. What should be on the frame? What value should be on the frame? Let me just point to the correct spreadsheet so that it's visual. Okay, so you should be able to work this out. Okay, don't try anything too complicated like this. In this case, the C program is going to call the function f 4 times, but I'm just going to call it with one single node first, just to make sure that that works. So when you're debugging your program, do the same thing. Always test the simple cases first. Okay, basically the cases where it does not do anything recursively. If that works, everything works out as you expect, then you start to test the recursive cases. Because if the non-recursive case is not working, you don't need to bother with the recursive cases. There's no way the recursive cases would work correctly if the non-recursive one is not working. Okay, so I hope this is helpful, in terms of giving you some idea of how you can write this program and how to test it incrementally and also how to debug the program. The bottom line is you need to know what it is supposed to do so that you can compare the actual behavior of the program with what you are observing in the trace analyzer. I'm going back to the if you go to the general channel of this class, um, there is a discussion of a tool that Jonathan has developed. So Jonathan has written his TTP-ASM simulator, and it also has a trace output, at the same time. And from what I can see, the trace analyzer output is more readable compared to my spreadsheet approach. Because the spreadsheet approach leaves a lot of lines that are unused. So you can check that out. Okay, I am not developing that program, so I cannot guarantee anything. I mean, if I cannot guarantee my own code, okay, if I cannot guarantee anything about my own trace analyzer and my own assembler, I cannot guarantee anything about what other people have done. Okay, but I'm just telling you that there's an alternative. There you go. Um, all right, so I think I'm pretty much done with everything I want to say for tonight's lecture. There's no lab tonight because I thought, since most of you are still working on this program, I would leave you to work on the program using tonight's lab time. And I think, because I'm online during this time, it's really kind of a good time to, um, you know, write your code and try to debug your program. Um, Otherwise, it'll just be the office hours and whenever I can, get to the messages to help you out. Cool. Yes, I will be online tonight to answer questions. Basically from here to about 9:50. So there we go. Alrighty. So there's nothing else I need to say at this point. So basically, go ahead, don't procrastinate this kind of program. It really takes time to write and debug. I'm turning on, the webcam again because I want to show you my face of concern. If people have not started at this point to write this program, it's gonna be a rush, to the end. All right, so I'm gonna sign off, and I'll be back in about 10 minutes to answer questions. And keep in mind that I will not directly answer a question like, oh, this line of your code is wrong. It should be like this. I'm not going to do that, but I will ask questions. Okay, so just kind of expect that when you ask questions, that I'll be answering your question with another question. All right, I'll be back in 10 minutes, and see you in 10 minutes.